In this presentation, I'll be explaining first quadrant choppers, second quadrant choppers, and two quadrant choppers. Let us see the types of choppers classified based on the quadrant operation. Now, first quadrant chopper, that's also called type A chopper. And this is the circuit topology of a type A or first quadrant chopper, in which you can see that one, the average voltage across the load, that is always positive. Similarly, the average current through the load is also positive, meaning that this is the uh, current axis, current output current, and this is the output voltage, and always output voltage is positive and output current is positive. That is why that is operating in the first quadrant. Now we can say that one actually this current is proportional to, or you can say that mechanical quantity here, torque is the mechanical which is proportional to the current, and this is the speed which is proportional to the voltage. Therefore, this is a torque axis in mechanical uh, plane as such. Here torque as well as this is omega m. Therefore, here if you see that one, the product of electrical quantity V0 and I0 is positive. Therefore, that is actually is a motoring operation. That is T into omega is positive, or it is called, and we can say that omega is positive if you omega is in this line. So it's called forward motoring region. Actually, it is working in this called forward motor quadrant region. And here the working of this one, let us see that one. This is a circuit topology, and in which this is a chopper switch as such, and this is a freewheeling diode, and this is a load as such. And here when the switch is closed, here you can see that one, the diode is for reverse bias, because we are getting a positive voltage, reverse bias, and the circuit is like this one, and the corresponding output voltage, the voltage across the load is same as the input voltage V. That is why during T on period of the switch, here you can see that one, output voltage equal to V. And when switch is off here, during that period, this is a highly inductive load, that energy will, in that inductance, the energy will be stored here. And when the switch is off here, that inductance will be driving a current through this path or through the freewheeling diode. Or freewheeling diode will be forward bias, and that will be circulating a current. And during that period, the voltage across the load is again zero, but there will be a current flowing through the load as such. Therefore, there's a continuous current is flowing through the load, and during the on period, the output voltage equal to V, and during the off period of the chopper, the voltage drop is, of course, it is the diode drop we are neglecting. You will be getting almost zero voltage, and that will be continuing. Therefore, this is the instantaneous value of the voltage across the load, and the average voltage, that is the dotted line, represents the average voltage that is represented, and that average voltage can be calculated as integrating this one, or we are calculating this area that is distributing over the time period T. For this area, you can calculate as V into T on, is that is called this area, that divided by T, or that is actually 1 by T integral 0 to T on into V0 dt, or T on divided by T into V, or D into V, where D is the duty ratio, which is equal to T on by T. Therefore, the average voltage across this load is equal to, always that will be positive, because only here you will be getting a positive voltage across the load, and the average value of the both, and as well as the current is also positive. Always the current will be in the positive direction. The average current is equal to positive. Therefore, average value of both load voltage and the load current, that is V0, I0, is always positive. That is, it is working in the first quadrant. And power flow is always from the source. If power flow is, because the, as I told you, this is actually in mechanical plane asset, this is the torque axis and this is the omega m axis. The product of torque into omega is called the power, mechanical output power. Therefore, in that case, the electrical power is being converted into mechanical power. The power flow is from this source to the load as such. Therefore, power is flowing from the source to the load, and this chopper is also called step down chopper, because output voltage is less than the input voltage, which is equal to D times V, and that is also step down chopper. And the chopper as an average output voltage V0 is always less than input voltage of this, because this is a step down chopper. That is why this average output voltage will be less than the input voltage, and the power is flowing from this this source into the load. So that is our first quadrant operation. That is called also that is called forward motoring region. Now let us see the second quadrant chopper. That's also called type B chopper. In that one, in this chopper, we are considering the load must contain a DC source or a battery, that is back EMF of a DC motor can also be considered. Therefore, this type of load, this will be working. Type B chopper is that. Therefore, that is a load inductors in back EMF, or just like if you are neglecting the armature resistance, or simply DC motor can be considered as this load as such. And here the switch is coming across this one, and the diode is polarity is like this one, and this is connected to the source. And when the switch is on, that is when switch is closed here, there will be that due to this E, there will be a current in this direction, or that will be storing the energy in the inductance. Energy will be stored in the inductance, and of course the current is, you can see that one, it is opposite to the, actually I0 is positive like this one, but the current is opposite to that one. The negative current is getting, and here the voltage across the load is equal to 0 when switch is on here. And when switch is off here, this whatever the energy stored in the inductor, that will be feeding a current in this direction to the, through the diode will be forward bias, and that will be returning back to the source. Therefore, that is the concept of regenerative braking of the DC motor. Here, when switch is on, the energy will be stored, will be circulating current, energy stored in the inductor. When switch is off here, whatever this energy stored, that is returned back to the source through this path. Through this path, it is going through the diode. For in that case also, current is negative, that one. For the always current is negative, but if you take the during that period, what is the voltage coming here? During that period, this voltage is same as this voltage, because this is conducting, the voltage is same as the input voltage. Therefore, the average voltage can be calculated. When switch is on, it will be getting a 0 voltage. When switch is here, when on, 0 voltage, and when switch is off, you will be getting the input voltage. Always the current is negative, but average voltage will be positive. Therefore, that is the second quadrant operation. The average voltage will be positive, and the average current, the current that is flowing here, that is always negative. That's the second quadrant of operation. It's actually, it is a regenerative braking, or it is called reverse power flow as such happens during this period. Or here regeneration is there. So as I told you, this is the torque axis, and this is the omega axis in the mechanical plane. Therefore, omega is equal to positive. That is, so it's the forward, and torque is negative. It's called braking operation. Reverse torque is coming here. For actually, it's a regenerative braking operation happens in the type B chopper. Depending upon the position of the switch here, when S2 is on, the load voltage V0 is equal to 0, and the battery voltage E drives a current through L and S2. Through this one, it's driving a current through this path. And during the on period, whatever the energy stored in the inductor during the inductance is stored in the inductor. That is, during the on period, the L stores the energy. That is, when switch is on, energy will be stored in the inductor. And when S2 is off, when the switch is off here, the energy stored in the inductor, whatever the stored inductor, is returned to the source through the diode too. Because when, in order to continue as per the Lenz's law, in order to continue this current here it will become plus, and here it will become minus, or the diode is getting forward bias, and the energy stored in the inductor is returning back to the source through the diode. Therefore, when S2 is off here, the energy stored in the inductor L is returned to the source through the diode D2, and when the chopper is on, that is, when the chopper is on and off, always the current flows out of the load. For whether when the chopper is on, the current is going like this one through the load in the opposite direction, and when this is off also, the current is in the opposite direction. That is, always the current is negative. Therefore, V0 is positive and I0 is negative. The power flow is from the load to the source. If you take the product, that one, I0 and V0, it's negative, meaning that the power is flowing from this load into the source as such. Therefore, since the power flow is from the load to the lower voltage to that one, source of, to the load of lower voltage to the source of higher voltage, type B chopper is always known as a step-up chopper. It is called a step-up chopper as such. Therefore, since the power flow is from the load, that is from the load side into the source of, that is, this chopper is also called a step-up chopper. Now let us see a two-quadrant chopper. That is, two-quadrant means there are the two types of two-quadrant chopper. One is called type C chopper. Next one we call type D chopper. In type C chopper, it will be operating in either in first quadrant or second quadrant. That is, first quadrant or second quadrant will be operating. And this is the circuit topology in which this is a DC source, and the switches are like this is marked like the S1, and of course the D1, and this is S2 and D2. Here S1 and D1 operate in the first quadrant. To make it operate in first quadrant, S1 and D1 is working, and to make it operate in the second quadrant, S2 and D2 are working. And this is the back EMF of a DC motor, and this inductance, armature resistance is neglected. Therefore, this is the load as such, and this is the average voltage across the load equal to V0, and average current, or that current flowing through that, I mean that is the voltage current going through the load is equal to I0. Therefore, V0 and I0 here, it will be, the voltage will be always positive, but current will be either in positive or negative. That is two quadrant, first and second is operating. That is called type C chopper. Therefore, the same circuit is shown here, especially when the load is, just to show that one, it's a armature resistance are considered. This is the motor load as such, DC motor load, and in that one S1, D1 and S2 and D2. Therefore, this is the same circuit topology shown here, and here we can see that one, always the output voltage, that is output voltage is always positive because of the presence of the freewheeling diode D1 across. Always the voltage here will become positive. It never goes to the negative, because once it is going to negative, this diode, that will be driving this diode and will be getting a zero voltage. For the output voltage will be always positive because of the presence of the freewheeling diode D1 across the load. And the load current may be either positive or negative. The load current can be either it is in this direction, or it is in the opposite direction. The load current can be either positive or negative. Here positive or negative, and here always the voltage will be positive. Now in the mechanical plane, as I told you, here this is the torque axis, and this is the omega m, angular velocity axis or angular speed axis as such, omega m. Therefore, here the product of T into omega m here is equal to positive, or the product of current and voltage is positive, meaning that it is the mechanical output is, or here during this portion the electrical power is converted into mechanical power, or that is the power flow is from the DC source into the motor. Therefore, that is first quadrant operation. Now, if the current direction is opposite here, you can say that current is opposed to that one. We can say that you'll be getting a negative torque, because that depends upon the armature current direction is negative. Here the negative torque will be producing, and the omega or the speed will become positive, or voltage omega is proportional to the voltage. Therefore, omega is positive or VA is positive. The product, if you say again calculate T into omega or voltage into current, you can see that one, it is negative, meaning that the power is flowing from the load side into the source side, or that is working in the second quadrant. Therefore, this is called a forward motoring case, in which the power is flowing from the DC source into the motor, and this is called reverse braking. It's a reverse brake. So forward braking, not reverse, because speed omega m is not changing. It's forward only. Forward braking, or just also regenerative braking. The forward braking, because omega is positive itself. Therefore, it's a forward braking as such. In that one, for example, in this we'll see the equivalent circuit when during the first quadrant operation as well as the second quadrant operation in the next slide. And the load current may be either positive or negative. It can be either positive or negative, but always the load voltage will always equal to positive. Therefore, it is working either in the first quadrant or in second quadrant. And when it is working as a second quadrant, the power is flowing from the DC source into the motor. That is called forward motoring operation. And when it is working the second quadrant, the power flow is from the motor into the source, or that is called forward braking or regenerative braking happens for the second quadrant operation. Now, continuing the two quadrant type C chopper, first and second quadrant, as we have already seen, first and second quadrant. In order to work it as a first and second quadrant, first quadrant operation, it is the devices are S1 and D1. That is, this is the equivalent circuit to work in a first quadrant operation, that is forward motoring operation, in which we can see that when S1 is closed here, this diode is reverse bias, you will be getting a positive voltage V here. And when S1 is open here, because of the inductive energy here, there will be a voltage which is forward bias in diode, plus here and minus here, and there will be a circulating current in this direction, and the voltage equal to 0. Therefore, we can see that in both cases the current is flowing in this direction. Therefore, I0 is same, I0 is positive, as well as average voltage is given by, when it is S1 is on, it is V, and when S1 is off, it is equal to 0. Therefore, the average voltage is given by, as we have already derived, it is equal to D times V, or it is the step down action is taking place, that is in the first quadrant. In that case, the average voltage is equal to positive, and average in current is also positive, and the product voltage into current is positive, or in mechanical quantity T is positive. This is the axis, torque axis, and this is omega m axis. T into omega m is positive, or meaning that it's a mechanical output power is positive, mean the electrical power is converted into mechanical power, or that's called forward motoring operation. That is the first quadrant operation. And second quadrant operation, we'll be using the second S2 and of course D2 is using. So this is the equivalent circuit of this one. This is a two quadrant chopper. In the equivalent circuit corresponding to the operation of the second quadrant is S2 and D2 will be coming. Similarly, we can see analyze that one when what is the here we can see that one, whatever be that one, average voltage will be positive. When S2 is closed here, you can say that voltage equal to 0. Voltage equal to 0. When S2 is open here you can say that one diode is conducting, you will be getting a positive voltage, because that through this diode the circuit coming, or here getting positive voltage. Therefore the average voltage will also here it is equal to positive only. Here average voltage V0 will be positive. And but the current, we can see that one, when switch is closed here, the current is circulating like this one. Therefore, the I0, actual current I0 will be negative in that case. Similarly, when this is open here, in order to continue the current, it will be taking the path of D2. Therefore, here also the current is negative. Therefore, when S2 and D2 are working in that one, that is the second quadrant operation, always you can see that current is opposite to this I0, whatever shown here. For a negative current happens, but average voltage is all positive. Therefore, when S2 and D2, the average voltage is always positive, but average current is always negative. You can see that it will be negative. Therefore, the product voltage and current is negative, meaning that negative power means that reverse power is flowing. Or another way, we can see that one, T into omega. This is the T axis and this omega axis. T, product of T into omega is negative, means that here this power, whatever the power here, that motor braking action is taking place, the power is flowing from this to the source. That is the braking action, or that's called regenerative braking, or it's also called reverse braking, or reverse, because no, not reverse braking, or forward braking. Forward braking, because always omega is positive here only. Therefore, it is a forward only, but the product is negative, means that braking action is happening, or reverse torque is produced, because the current polarity is reverse, means current polarity decides the torque direction here in this case. Therefore, here as current is reverse, here we can of course the torque will become negative. Armature current is negative, because for a separately excited motor, as armature current is reverses, the reverse torque will be producing, or braking action take place. For this is a braking region of operation, that's a regenerative braking, and this is a forward motoring operation. Therefore, this circuit will be working when S1 and D1 these are operating, it will be working in the first quadrant. When S2 and D2 are working, that is operating in the second quadrant. First quadrant of operation is called forward motoring, and second quadrant of operation is called reverse braking, or in that case the this braking action is taking place for the motor in the second quadrant. See, another type of type D chopper. It's also two quadrant chopper. This is called a type D chopper. In that case, previously it was first and second, but here it is first and fourth. It is working either in the first quadrant or fourth quadrant. First quadrant is again, it is a forward motoring operation, because T and omega, if we say that omega is positive and the product of T into omega is positive, that's for motoring action. Forward also omega m. That's for this is called forward motoring region. But in this case, you can say that one here the voltage is negative and current is positive. Again, the product V into I is equal to negative, or that's called a braking action is there, as well as the omega. You can say that V is positive, negative means that omega is negative, or it's called reverse braking action is taking place. Therefore, in this case, in this type of, this is the chopper configuration for that second type D chopper. So it's a two quadrant chopper, and here the position S1 and this is S2, and here D1 and D2 load is connected between this one, and this is the DC source. Now let us see that one. Again, we can see that one. This is working S1 and D1. Here we can say that, I mean, when S1 is on here, when S1 is on, that we can get here S1 and S2 are on here. Say that one, when S1 here, S1 and S2 are on, because S1 and S2 are on here, you will be getting a positive voltage. Here you will be getting a positive voltage. And when D1 and D2 are on, that is when S1 and S2 are off, D1 and D2 will be conducting. In that case, we can see that one here. Again, this polarity is coming to here, and here this polarity is coming here, or negative voltage is getting. But always the current is in this direction only, because diode D2 also current in this direction. Therefore, the current through the load is same in both cases. That is why we can get either one per second. But the voltage polarity reverses. When S1 and S2 are conducting, the voltage polarity plus here and minus here. And when D1 and D2 are conducting, the polarity, that is when S1 and S2 are off, D1 and D2 will take care. And in that case, you'll be getting here plus, here you'll be getting negative, because this negative polarity comes here, and here the positive polarity comes, or reverse voltage is kept. Therefore, that is either to be working in the forward motoring case, or this is the reverse braking region for first quadrant and fourth quadrant. In this chopper, load current is always positive, and the load voltage may be either positive or negative. For output voltage, that is average output voltage V0 equal to V when S1 and S2 are on. When S1 and S2 are on, this voltage is equal to V0 is same as the V. When S1 and S2 are off, the diode D1 and D2 conducts. D1 and D2 are conducting. Average output voltage when D1 and D2 conduct, here we can say that one a negative voltage comes here. Here plus comes here, and here minus comes, a minus V comes here. Average output voltage is the positive when chopper is on, and T0 is more than T0. Therefore, here we are getting when D1 and D2 are conducting, the voltage across the load is equal to minus V, and when S1 and S2 are conducting, the voltage across the voltage is equal to plus V. Therefore, depending upon the the value of T on and T off, the average voltage will be either positive or negative. We'll see that waveform in the next slide. Therefore, the average output voltage V0 is negative when the on period is less than the off period. And when on period means when S1 and S2 are, that is on period, when they are conducting on period. If that period is less than the period during which the diode D1 and D2 are conducting, in that case, the average voltage will become negative. In other case, it will be positive. Therefore, the load current will be always positive. You can see that one, when S1 and S2 are conducting, we can see that load current is in this direction. When D1 and D2 are conducting, again the load current is same direction. Therefore, the load current polarity does not change, or always it is positive. But the voltage, we can see that when S1 and S2 are conducting, plus here and minus here. When D1 and D2 are conducting, here plus and here minus. Therefore, depending upon the on period and off period, the average value of the output voltage will be either positive or negative, but the current is always positive. Therefore, it will be working either in first quadrant, which is called the forward motoring, or in fourth quadrant, it is called reverse braking. Now, continuing the two quadrant type D chopper, that is first quadrant as well as fourth quadrant, forward motoring as well as reverse braking or reverse regenerative braking, that is this region, that is first and fourth quadrant. And we can see that always the current is positive, but the voltage will be either positive, or average voltage will be either positive or negative. Now let us see the waveform as such here. And the two cases happens here. Here the on period is more than off period. This is the on period during which the S1 and S2 are closed, and this is the during which the diodes are conducting. We can say when S1 and S2 are closed, here you can see that one, the average voltage, the voltage across the load equal to plus V. When D1 and D2 are conducting, the voltage equal to minus V. Therefore, in this case, T on is more than T off. Now, if you take the average voltage here, we can see that one, average voltage is nothing but you take the average area of this one. This is a positive area, this is a negative area. You take the average area of that one, you can say that average area will be positive. Or, take the summation of this area, positive area, negative area, and then divide by this time period T. That's called the average voltage. For the average voltage will be positive when T on is more than T off. Therefore, the corresponding current is that when T on is going, the current is building up here. And when T off, during T off period, the current is dying out. Therefore, here the current is in the negative direction. That happens because you'll be getting a here negative voltage. When the voltage is negative, the current is dying out. Therefore, this is the current through the load as such. But always you can see that one, it is positive. The current is average value. You can see that one, average value of the voltage is positive. But average value of the current, we can say that depends upon the magnitude of T on and T off. If in this case T on is more than T off, therefore the average voltage will be positive. But in this picture, we can see that one, T on is less than T off. Now, if you take the average voltage, when T on is during the on period, we'll be getting plus V. And during the off period, because diode D1 and D2 are conducting, and during that period, the voltage equal to minus V. Therefore, this area and this area is added, and that is distributed over the time period T. We can see that one, since this area is more than this area, then average value will become negative. Therefore, when the off period is more than the on period, the average value of the voltage across the load will become negative. When on period is more than off period, the average voltage across the load is equal to positive. Therefore, you can make either average voltage equal to positive. It's called the forward motoring operation. In that case, current is positive, and average voltage can be brought to negative by making T off more than T on. But in both cases, we can see that one, this is the current flowing through the motor, or that load as such. Therefore, always the average value of the current is positive. Therefore, that this is the current is positive, and we can say that again the product is equal to negative. Therefore, that is the reverse regenerative braking or reverse braking operation is taking place, either first or second. And the average output voltage equation for that one, from this one looking to that one, average voltage can be calculated as V into T on, that is this area, here minus V into T of, for the total area is calculated, that is divided by the total time period T. That is the, for V into T on minus T off divided by T, or V into T on by T minus T off by T, V into T on by T minus T off, I am writing it as T minus T on divided by T, or T on by T equal to D. Therefore, V into D, T minus T by T, it is equal to 1 minus of 1 minus, again T on by T equal to D, or V into D minus 1 plus D, or V into 2D minus 1. Therefore, the equation for the average output voltage is given by the input voltage V into 2 times the duty ratio minus 1, V into 2D minus V. Now let us see that one. If say D equal to less than 0.5, you will be getting the average less than 0.5, you will be getting a negative average voltage. And if D is more than 0.5, you will be getting an average of positive value. Therefore, if D is more than 0.5, V0 is positive. And if D is less than 0.5, V0 is negative. Average load voltage equal to negative. Therefore, it can be operated, if average voltage is positive, it is working in a forward motoring operation because torque is positive. Omega is in this direction. In mechanical plane, it is torque, and this is angular speed omega m as such, and T into omega is positive. Therefore, that is forward motoring case. But when voltage is negative, you'll be getting omega is negative and torque is positive. Therefore, T into omega is negative, or you can say that reverse power flow happens from the load to the source, or that is called braking operation. That is called, of course, reverse braking operation is taking place. Therefore, in DC type D chopper, it will be either in forward motoring operation or reverse braking operation. Therefore, in type D chopper, if the on period is more than off period, the average voltage will become positive, and of course average current is positive. We will be getting operating in first quadrant operation. And if on period is less than off period, average voltage is negative. For average voltage negative, but current is always positive. It is operating in the fourth quadrant or reverse braking operation. In terms of the duty ratio, as we are seeing, if D is more than 0.5, the average output voltage equal to positive, or that is working in the first quadrant, or it's called forward motoring operation. And if D is less than 0.5, you substitute that. If D is less than 0.5, you can see that average voltage, for example, if say D equal to say 0.2, then V into 2 into 0.2 minus 1, will be getting a negative quantity. For the average voltage will become negative. Therefore, the average voltage will become negative, but current will be always positive. The product is negative, voltage into current plus negative. Or we can say that in mechanical quantity, this is a torque axis, this is omega m axis. Therefore, torque is positive, omega m negative, T into omega is negative. Therefore, the mechanical output is negative, means that power is flowing from the load into the source, or that is called braking operation, or that's the reverse direction, reverse braking region, fourth quadrant.